Hello everyone. In this video, we're going to look at t-tests. And a t-test is used when population parameters are unknown and you have to estimate them with sample statistics. So unlike the z-tests we did in chapter 8, we're not going to be given population information. So for example, we might not know the population standard deviation. And so instead, what we do is we estimate it with the sample standard deviation. Now obviously, anytime we make an estimate, there's a chance of being wrong. And so what we can do then is to figure out how good our estimate is and so forth. So I want to jump right into that with a problem, and we'll do two of them to look at some of the differences you might encounter. So this one says, to evaluate the effect of a treatment, a sample is obtained from a population with mean of 30, and the treatment is administered to the individuals in the sample. After treatment, the sample mean is found to be 32.3, with a standard deviation of 3. If the samples consist of 36 individuals, are the data sufficient to conclude that the treatment has a significant effect using a two-tailed test with alpha of 0.05? All right, so essentially, it's a basic hypothesis test where you have some population that has a score of 30 on average, and you give 36 people a treatment, and their scores on average are 32.3. So the difference here is that we're not given the population standard deviation. Instead, we're given the sample standard deviation, this value of S. And so, importantly, a lot of times in the real world, social scientists don't know about population parameters. Sometimes populations are gigantic. For example, humans, there's billions of people, so you don't often know population information. So what we do instead is we estimate those values with sample statistics. Whenever you do that, you cannot rely on a z-test. We use a t-test, which relies on the t-distribution. And this basically has proportions that correspond to estimated values associated with the normal curve. And so make sure you have your t-distribution handy. But in many ways, these types of questions are similar to the chapter 8 questions as well. And so let's get into it. At the end of the question, it says, calculate Cohen's d and r squared as measures of effect size and compute a 95% confidence interval. So there's a lot going on here, but let's take it step by step and we'll see how it goes. So step 1, as always, should be your hypotheses. We're doing a two-tailed test, and so the hypotheses are going to look like this. The null hypothesis, as always, is the boring one. It says nothing's going to change. People on average have a score of 30. If you give a bunch of people a treatment, nothing's going to happen. It's still going to be an average of 30. On the other hand, the alternative is the one that says, no, the treatment is going to be effective. Something's going to happen. So on average, the mean will not be 30. All right. So we have 36 individuals in our study. And the next thing we need to do is identify the critical values of t. And if you look at your table, one of the things you'll notice is up here you have your alpha levels. Here is df. We need our degrees of freedom, which is n-1. So let's just calculate that real quick. df equals 36 minus 1, which of course is 35. And we're using an alpha of 0.05, two tails. So let's go ahead and find our critical values of t. Now what you'll note here is that 35 is not listed on the table, and that's probably because our textbook wanted to conserve space. So what we're going to do is use the value below it, numerically speaking, which is 30. So 30 degrees of freedom on the table, and we want to find a proportion of 0.05 in two tails combined. If it was a one-tailed test, we would use this one right here, proportion in one tail. But this says proportion in two tails combined, 0.05. Okay, so it looks like the value is 2.042. So here is 2.042 on this side. That's our critical value of t. And down here is our negative 2.042. Remember, this is a two-tailed test. So these are the critical regions of t. If the treatment causes a change that is 2.042 standard deviations away from the population average, which is standardized as 0 here, then we're going to say that there was a statistically significant change or effect or treatment. All right, so let's see what we have. The first thing to consider, just like in the previous problems in Chapter 8, you have to calculate your standard error. Here it is. We call it the estimated standard error because we are using sample values to estimate population values. Let's go ahead and calculate that, and then we can interpret it. So we have the standard deviation for our sample was 3, divided by the square root of sample size, which is 36. So 3 divided by 6 is 0.5. So what we can say is that due to random chance alone, you can expect a sample to have an error of 0.5 points. And now we account for that in our test statistic, which is t. So t is calculated as your sample statistic, the individuals who received your treatment, 32.3, divided by, subtracting your population value, which is the individuals who did not receive your treatment. This is the hypothesized value of your null hypothesis, 30. And then divide by 0.5, which is your standard error. All right, so 2.3 on top, the numerator, divide by 0.5 gives us 4.6. So the difference between those receiving the treatment and this hypothesized population value of 30 is 4.6 times larger than chance alone. That's the interpretation of that. The cutoff was only 2.042, plus and minus. So 4.6 is in the critical region. So our conclusion is reject H0. There was a statistically significant effect, a statistically significant change. So now what we can do is calculate effect size. You have two options when it comes to t-tests. The estimated Cohen's d, formula is up here for you, and r squared. And there's information in the module as well as the textbook on the differences between the two. But let's go ahead and calculate and interpret them right now. So d, estimated d is sample mean 32.3 minus population mean of 30 divided by the sample standard deviation of 3. And that gives me 0.77. And so we would probably label that medium to large, since it's in between the medium and large values. M to L, medium to large. All right, the next thing we can do is calculate r squared. R squared is another alternative for effect size. And so its formula is right here. You take your calculated value of t and square it, and then divide by t squared plus degrees of freedom. So it looks something like this. 4.6 squared over 4.6 squared. Whoops, got to use an eraser here real quick. 4.6 squared plus degrees of freedom, which was 35. Let's go ahead and do that. So it looks like we're getting 21.16 in the numerator. $56.16 in the denominator. And that gives us a total r squared value of 0.41. All right, so according to r squared interpretation values, large is 0.25. So this, we could say large or very large, since it's above that cutoff value. Now, one thing to consider is that for Cohen's d, we got medium to large, and for r squared, we got very large. that can happen. And that is because, as you are hopefully reading in the textbook as well as the module, Cohen's d is a measure of distance. It's how many standard deviations did the treatment cause a change in. It's how many standard deviations did the treatment cause a shift. R squared, on the other hand, measures how much variability is accounted for by a treatment. So 0.41 is 41% of the variability. 41% of the variability in scores among these 36 individuals is explained by the treatment effect. So they're measuring different things, but they're both an indication of effect size. All right, last but not least, it says compute a 95% confidence interval. So the idea is that the treatment clearly caused a statistically significant effect. That's why we rejected age 0, and it was a large effect, a medium to large, or very large, according to R squared. So what we're going to do now with confidence interval is estimate the true population value for everybody who would receive this treatment. If everybody received the treatment, what's our estimate of the true population value? And so what you're doing with this confidence interval is you're going to calculate a range from a lower number to a higher number that you will be 95% confident the true population value falls within. And so let's go ahead and do that. The formula is right here for you. Take your sample mean, which was 32.3. And then it says add and subtract. That's how you get the interval, the upper and lower numbers. So we add and subtract the following. T. What T? Importantly, this T is the one from the table, the one that you used for your critical values. And again, not again, but one way to remember that is you had a positive and negative value there, and there's a positive and negative value there. So for two-tailed test, it's kind of, I think, easier to remember that. But anyway, let me just say one thing, that the t value for r squared is the calculated value, the one we calculated with our test statistic, whereas the t value for the confidence interval is the one from the table, and that was 2.042. And we multiply that by the estimated standard error, which was 0.5. All right, so let me go ahead and calculate this. Essentially, we're getting 32.3 plus and minus 1.02. So the lower value is 31.28. And the upper value is 33.332. All right, so the interpretation is as follows. We are 95% confident that the true population value of individuals with treatment is between 31.28 and 33.32 points. The last thing I want to say about this problem is, why did we compute a 95% confidence interval? That is because that's the value that corresponds to an alpha level of 0.05. Alpha of 0.05 is essentially 5%, and so that corresponds to 95%. Together they make up 100%. When you use an alpha of 0.01, that most easily corresponds to a confidence interval of 99%. The reason that's nice is that you don't have to re-find your critical value of t. You can use the same t value as you did in your critical values as you will in your confidence interval. Okay, so there's the first question. Let's now turn to question number 2 in this video, another t-test. This one is based off of an actual study that was conducted in 2010. So some researchers, Weinstein, McDermott, and Roediger, report that students who were given questions to be answered while studying had better scores when tested on the material compared to students who were simply given an opportunity to reread the material. In a similar study, an instructor in a large psychology class gave one group of students questions to be answered while studying for the final exam. All right, so essentially what's going on here is we're making an experiment. We're going to see if exam scores are different, comparing individuals who get practice questions versus those who do not. So the treatment is whether or not students got these study questions to go over and practice their questions. The overall average for the exam is 73.4. That's just the regular average. But the 25 students who answered questions had an average of 78.3 with a standard deviation of 5.4. For this study, did answering questions while studying produce significantly higher exam scores? Use a one-tailed test with 0.01 alpha, and then calculate effect size and a confidence interval. So we're going to do a one-tailed test now, and the reason for that is we have a prediction about the direction of the effect. We specifically expect that students who get to practice with sample problems, that their scores are going to increase, not just change, not just be different, but actually be different in the higher direction, which means we're doing a one-tailed test. All right, so step one is your hypotheses. And as I was saying in an earlier video, for a one-tailed test, I tend to start with my alternative hypothesis because the alternative hypothesis is the one that has your prediction. And so the prediction is that you expect scores to increase. They will be higher than 73.4. 73.4 is what people had on average without the treatment, and we expect the average to increase. All right, and therefore the null hypothesis says no, they will not increase. They might even go down or they'll stay the same. All right, we're using an alpha of 0.01, one-tailed, and so I'm going to shade in my critical region, 0.01 here, and I'm going to go to my t-table. Before I do that, I need my degrees of freedom. And so there are 25 people in the study. 25 minus 1 means there are 24 degrees of freedom in this study. So I go to my table, find 24 degrees of freedom. There it is. The actual value is listed this time, so we don't have to worry about that. 24, and I scroll over to the correct alpha level. And here it is. 0.01 is the proportion in one tail. So 0.01, I look at this column here, and it looks like where 24 degrees of freedom matches that, I see a value of 2.492. That's our critical value of t. All right, so next let's actually find, let's calculate our statistics, and so that we can make our conclusion. So the next step should be your standard error. And that will be calculated as 5.4 over the square root of your sample size. So 5.4 divided by 5, 1.08. And then we can use that to calculate our t-value, our test statistic. So the individuals with the treatment had a score of 78.3 on average. Compare that to those who did not, which was 73.4, and then divide by error, which is 1.08. Looks like a test statistic of 4.54. And 4.54 is in the critical region. It's larger than 2.492. So I'm going to conclude the following. Reject H0. In other words, that's terrible. In other words, there is a statistically significant effect as a result of this treatment. So then follow that up with effect size. How big is the effect? So according to Cohen's D, let's determine that. 0.91. And so that is greater than 0.8. So you might call that very large or just large. There's no real one way to do that. Let's then calculate r squared. By the way, on the exam, you probably won't have to calculate both for every problem, but it's good practice, so that's why we're doing it here. Well, let's calculate this. So 4.54 squared over 4.54 squared plus 24. 24 is our degrees of freedom. .46, and the large value of r squared is 0.25, so that's much larger. You could say again very large or large. Great. Finally, let's go ahead and calculate the 99% confidence interval so that we can estimate the true population mean. And so let's go ahead and do that. We have our sample mean of 78.3 plus and minus your critical value of t, 2.492, times the estimated standard error of 1.08. .69. So let's see what we have here. .61 is the lower end of the range, and the upper end of the range is 80.99. So we are 99% confident that the true population mean for those receiving this treatment is between 75.61 and 80.99 points. All right, so that concludes this problem. But one thing I want to do to end this video that I didn't do in the last question is to write out the conclusion statement. And this is how something like this might appear in a published report. So a researcher, if they were to publish their work, they don't include what you're seeing here. They try to formalize it in the following way. And so here's what we might say. The data suggest a statistically significant increase in exam scores, comma, and here's what I'm going to do. I'm going to put T, because I did a T-test. In parentheses, I'm putting my degrees of freedom, which is 24, and then I'm putting my test statistic value, which was 4.54, comma, P is less than 0.01. Now, as written in the module and the textbook, that little part right there tells you two things. It tells you what was the alpha level that was used, which was 0.01, and in this case, P stands for the probability of making a type 1 error. And briefly, in review, a type 1 error is where you reject H0, but you shouldn't have. In other words, you claim to find an effect, but there actually isn't one. And so we rejected H0, so P is less than 0.01. When you fail to reject H0, P is greater than 0.01. In other words, you would write it in the opposite direction if you fail to reject H0. So P is less than 0.01. I'm going to put my estimated D equals 0.91. and I'll put large in parentheses there, and then R squared. In this program, I can't use superscript, so I just put R2 here. It's kind of annoying, but you do want the superscript like it's shown here. That was a 0.46. We could also say large there. And then finally, 99% CI, which is confidence interval. I'm going to put these brackets, 75.61 and 80.99. All right, so there you have it. That is the conclusion statement for this problem here, as it might appear in a published document. Excuse me. Okay, so I'm trying to think. I think that's everything I wanted to cover for the introduction to t-tests. So these are chapter 9 questions. Move forward in the modules and we'll look at more advanced t-tests.